So when you're dealing with a trillion anythings, you're going to have defects. You can't expect to perfectly manufacture 10 to the 24th cells, no matter how good your manufacturing is. You can't expect to manufacture that many cells without some of them being defective. And even if they're all manufactured perfectly, they're going to have runtime failures. There's going to be upsets from just random perturbations in the values stored in memory circuits and so on. So there's going to be defects. We have to deal with them. We can't ignore them at this kind of scale. So how can we deal with defects in a cell matrix paradigm? Well, one thing we can do is we can test a region of cells. So for example, let's suppose that this is some region of individual cell matrix cells, and we would like to know if all of the cells in here are operating properly. And let's say we're starting up here and we have access to these two cells. What we can do is we can use the C and D inputs on this cell to load a particular configuration into it. We can load in, for example, the truth table of all ones, and then we can keep it in C mode and read the D bits that are coming out and make sure we're seeing ones. That will tell us if there's any bits in the truth table memory that are stuck at 0. Then we can load the truth table with zeros, try to read back zeros. That'll tell us if there's any bits that are stuck at 1. We can configure it next to be, say, an inverter to take whatever data value is coming in, invert it, and send it back out. And now by loading in a pattern of 1s and 0s and looking for the inverse coming out, we know that that part of the truth table is working correctly. We know that the data inputs and outputs are not stuck at 1 or 0. And we can do a series of tests. Depending on what kind of concerns we have for particular defects, we can do different tests, different analysis, and eventually hopefully decide that this cell is working properly. And we can do a similar series of tests down here. Once we know that these first 3 cells are working properly, we can use them to access any of these 3 cells. So this is just straight wire building, and the wire building lectures talk about this in great detail. But basically, once we have control of these 3 cells, we can build a wire that moves around throughout this region and gives us control over any cell that we want. So we can repeat these tests. We can test this cell, we can test this cell, and if those are working properly, we check them off, and we use these sets of 6 cells now to give us control over this region. So as long as we know that what's outside of this region is working properly, we can test each of these cells and decide with whatever degree of confidence we need whether or not the cells are working properly. If they are, we can use those cells to test for cells that are further inside this region. And we can move through here, we can make turns and come back and test like this. We can do things like test cells from other sides. And again, it depends on what kind of concerns you have for particular errors, how you plan to use the cells in this region, but we can do a number of different tests and inspections on these cells, and eventually either decide that there's a defective cell in here or decide that the entire region is working correctly. And once we know it's working correctly, we can incorporate these cells into subsequent test circuits. So in the case of a supercell network, what we're doing is we're testing a region that's going to become a supercell. We test each of the cells. If we find that they're working correctly, we say, great, we go ahead and we configure this region as a supercell, and now we have a bigger supercell network that we know is defect-free. And we can use that to test regions adjacent to that perimeter. And if we find a defect, then we know not to use the cells in that region to do subsequent tests. So this protects us from the possibility of building a test circuit on a defective cell. Because we're testing the cells ahead of time, we're only building the test circuitry once we know the cells have been tested correctly. Now this is dealing with manufacturing defects. This does not address the issue of runtime defects. That's a totally different issue that has to do with redundancy in comparison and coming up with ways to detect errors within your circuit's behavior and then doing some kind of mitigation of it. But this is just dealing with manufacturing defects for now. So this lets us test a region and lets us build supercells only on regions that we know are working correctly. So what can we do with that? Well, let's go back to our original example. Let's suppose, first of all, that this first region, we've already decided that this is working correctly. And so this is our initial seed, our first supercell. Remember, the next thing that we did was we sent configuration information into here to configure the cells in this region to be another supercell. But before we do that, we do these test patterns. We test all of these cells. And let's suppose that we find out that this cell all the cells in here are working correctly. We go ahead, we configure that as a supercell. Now the next thing we did was configure regions to the south. So we're going to configure this region and this region to be 2 more supercells. And again, first we do this pattern checking, this fault checking to see if there's any defective cells. And let's suppose that this region all contains good cells, but this has a defect somewhere inside it. At some point when we're building our scan paths and we're testing a cell, we're going to try to configure this, say, as an inverter, and it's not going to respond correctly. And we're going to say, hey, there's a problem in here. So at that point, this cell knows that there's a problem in this region to the south. What it does is it activates what's called a guard wall on its southern edge. And this guard wall is a particular configuration of cells that basically prevents anything over here from interacting with anything to the north of the guard wall. And we build this guard wall inside this region that we already knew was working correctly. So we know the guard wall is going to operate properly and protect us from whatever's happening here. So this whole region is going to be considered suspect, and we're basically going to ignore it. Alright, so the next thing we do is we configure to the north, and let's just suppose that this configuration works perfectly. And in this case, we're also going to configure to the east, and that's not going to do anything at this point, or to the west, and that's not going to do anything at this point because there's nothing to the west. This is the edge of the matrix over here. So when we try to configure to the west, nothing's going to happen. It's just going to look like there's no space there. So now we're going to configure to the east again, and this cell will try to configure this region, and this cell will try to configure this region. But this cell, remember, it has no supercell to the right of it, and so it's going to try to configure this region. And it's going to do its scan tests and eventually hit this defective cell, and it's going to discover that this region to its east is defective, and it's going to activate its guard wall on the east. These 2 cells will configure correctly. Now we configure to the south, and this gets configured, and this gets configured. And then we configure to the north, and that will work fine. And we're assuming there's only 1 defect in the whole region here. But now when we configure to the west, this cell will actually detect that there's cells over here, and it will begin doing its test on this region, and it will discover that there's a defect in there, and it will light up its guard cell. Alright, now we configure to the east again, so these cells will light up here. And even though there's no direct path from here to here, there's an indirect path from this original input where our configuration information is coming in through this cell, this cell, this cell, to allow it to get configuration information and configure these cells to its east. This cell down here similarly will configure cells to its east, and assuming there's no defects in any of those, that will work fine. So we'll have this collection of cells now. And then we'll configure to the south, and that's going to go off the screen at this point, but this will configure, and this will configure, and let's suppose this is the bottom of the matrix. Now we're going to say configure to the north, so these cells would configure to the region above them, but this cell is going to see empty cells above it, and so it's going to try to configure in here. It's going to run its scan tests, eventually discover that defective cell, and activate its guard wall. At this point, a couple of things have happened. One, we've managed to continue to build this growing 2-dimensional region of supercells despite the presence of this defect. We have a full perimeter now in this 4x5 region, and this will continue to grow as usual. But the other thing that's happened is these 4 supercells surrounding it have all activated their guard cells around this region. And I've shown spaces in between these supercell regions, but in fact, the bottom of this supercell is connected directly to the top of this supercell and vice versa. So what's really happening is we're getting a continuous ring of these guard cells built around this region that contains at least 1 defective element. And this creates a guard ring, and this will prevent anything that's going on in here from affecting any of these good supercells around the guard ring on the outside. So we actually have a way to detect defects to isolate defects and to continue working around these defective regions and building this two-dimensional matrix. And we don't have anything like, loss of an entire column or row because of a single defect and so on. We're able to successfully fill in the regions in the same column or row once we're outside the defective region. And if there's a defect that's larger than a supercell, it works exactly as you would hope. You simply get a larger guard ring around whatever set of supercells you need in order to isolate that collection of defects, and then outside that guard ring the configuration continues. So that's a really, really high level view of how fault detection and isolation works during this parallel configuration. And again, it's an important aspect of the fact that there is no hardwired bootstrap mechanism, because were there a hardwired bootstrap mechanism, you might have a defect in that bootstrap part of your system, and then you wouldn't be able to boot anything. Because we're building our bootstrap system dynamically, and we're doing it by testing for defects before we extend the bootstrap, we're actually able to deal with a large number of defects as long as we have some initial region on the edge of this matrix that we know has good cells, which we can do by trial and error testing. Try to find a supercell size region that we can work with. Once we have that, our initial seed, we can boot the entire matrix with a collection of these tiled supercells, and we can do it efficiently. We can do it order square root of n or cube root n in 3D, and we can do it in a way that avoids defects. So that's the really high level view of defect detection and isolation. And in the lectures on supercells and on Medusa circuitry and on defect testing, we'll get into a lot more detail on this, but that's just sort of the 40,000 foot view.